Okay, so again, the purpose of this is to go through similar questions that you're going to see on the Regents. So hopefully you can find, hey, I know definitely 5 questions. When you sit for the Regents tomorrow, oh, it's that question. Oh, there's that question again. Oh, there's that question. As opposed to looking blanketly at 50 multiple choice questions saying, what do I do here? Oh, I see that question. That's what this is about. So in any case, here we go. So we're talking about types of question. I call this subatomic comparison. So in June 2012, here's the first question, and you can guess, and you should know that in your test, it's really important as you take it to understand that 1 through 30 goes through the entire year, and then 31 through 50 goes again through the entire year. So you should know where you are in the test. So I'm starting at number 1 or 31, expect atomic structure. If you're around 30 or 50, expect the last unit you learned, nuclear chemistry. To know where you are in the test is a good indicator and sometimes a good strategy of how to solve for this. So number 1, mass of a proton is approximately equal to the mass of a neutron. Now it seems some of you guys are like, well, why is that? Why am I going over that? Because people get the easiest questions wrong. I call these comparison questions, and some teachers don't use table O very much. So if I go to table O, great place to help you remember about particles. I've said this over and over again for those that don't know me, but a proton has a mass number of 1, and a neutron has a mass number of 1. So they both have the same mass. Okay, something to chew on. Number January 2013, which particles have the same mass? My gosh, proton and neutron. Okay? June, which particles have the same mass? I mean, it's the same question, actually. Some of these questions will be exactly the same. What's the mass of a proton? Now, that's weird. But protons are tiny, so don't expect 1 gram to be the answer. In my reference table here, let's get bigger. Okay. Sometime today. My proton has a mass of 1. Now, not 1 gram, it's called an atomic mass unit. You can't measure a proton. Actually, we can, but you can't measure with a regular scale because it's so tiny. So it's really an AMU, so atomic mass unit. Don't pick something. These are tremendously big, comparatively speaking, to a particle of a proton. So the 1U is actually sometimes called AMU, all right? Atomic mass unit. So that's the best answer. Which particle has no charge? Silly question. The bottom number is the charge number. So the neutron here has a charge of 0. By the way, neutral. Okay, I say atom, you say neutral. Atom. Okay, neutral means that it has no charge. Atoms have the same number of protons as what? Electrons. So obviously it's the neutron. All right, compared to the charge of a proton, the charge of an electron. Okay, now, some of your other teachers may not have done this, but a beta particle is essentially an electron. Bless you, meant it. Didn't lie about it. Okay? So a beta particle is also an electron. All right? So we put a 0 mass there, but it really has a mass that's really about 2,000 times lighter. Its charge is -1. So right off table O. And some teachers don't use this until nuclear chemistry, but it can be very helpful in the beginning part of your questions. So the charge of an electron has the same magnitude. Why? Well, a proton has a charge of 1. An electron, which is a beta particle, is -1. Okay? So they have the same size, just different sign. So same magnitude, opposite sign. I'm sorry, same opposites. Choice 4 is the answer. Easy questions? Yes. Ones that people get wrong, even the smartest students in the school? Absolutely. They get lazy. Okay, table O is your friend. Okay, wave mechanical model. This is the current model of the atom. You guys should be aware that there are 2 basic models of the atom that you pick on, and one that people tend to overlook and forget about. Forever, most of you guys think that the protons in the nucleus, correct, with neutrons, and some of you guys still think the current model of the atom has orbits in it. Electrons do not travel in circular paths around the atom. That's the Bohr model. And I hate to bore you on a hot day, but since that's what the Bohr model was about, sometimes called the Rutherford model as well. The current model still has protons and neutrons in it, but the electrons exist in a cloud based on standing waves. Okay? They still have the idea that electrons that are farther away have higher energy, and you have these leaps and their energy transitions that we'll talk about, another type of problem. But we're talking about regions of space. And these shapes, the honor students saw that some of these shapes are odd, but these were called the shapes called orbitals. And they're based on the idea that atoms exist as waves, not point charges. And these are standing waves, okay? So you'll hear the electron cloud model. Electrons acting as waves. They exist in places called orbitals, and that's what this question's about. In the Bohr model, you call them orbits, orbital. Sounds very similar. Why? Because what Bohr did was revolutionary. Electrons move an exact amount of energy called quanta from one position to the other. That's still true here. Okay? Still true here, except to give Bohr credit, we call it orbital. Okay? So the other thing is, because they're acting as waves, we have to use probability to talk about where they exist. So if you think of the current model, electron cloud, wave mechanical, you're thinking of orbitals, place where electrons exist, not orbits. They have regions of space based on probability, okay? And of course, they're acting as waves. So clearly, notice the words here. Most probable. That's based on probability. Notice the word orbital. Of course, it's an electron. And these questions are very similar. And my friends in chemistry, to get these wrong is absolutely, okay, terrible. An orbital, most probable region of an electron. They're over and over again, according to the wave mechanical model. Okay, most probable location of an electron. You probably will see this. I want you to identify it and laugh to yourself. That's so easy. I got this one. An orbital defined as a region with the most probable location, not of the proton, is of the electrons. See the circular path? 75% of the students pick circular path because they keep thinking the atom is this. No, that's the Bohr model. So it's a region for the electron location based on probability. Don't fall for that. You've seen these questions. Okay, here we go. Notice the circular stuff. They're throwing the circular stuff at you because you think it's that. But it's the most probable location of the electron. Do not get these questions wrong. I'm looking them over. I will find all of you in the summer when you're sleeping. Okay? No, it sounds pretty sketchy. Okay. Electron transitions. Okay, now, big question. This is an electron transition question. They want to talk about electrons. Now, we always draw this model, electrons going farther away, coming back. But it's an important question they love to know, love to ask about it. Now, it's hard to draw electron cloud models, so I'm going to use the Bohr model as an example, okay? Whether we're talking electron cloud or Bohr, okay? I don't know what I do with my thing here, so we'll have to go to the color. How about purple? Okay. Now, so what do we know? Whether I'm here or here, electrons that are closer to the nucleus have what kind of energy? Think about your mom, going to school with your mom all day. Okay, and she's right there. No matter what you do, she's right there. How are you going to act? Probably a little differently. Okay, you're going to be under what? Control of your mom. So you got low energy. Don't think you're going to do any interpretive dancing like Alex normally does, okay, without his mom, okay, around. So you have low energy. Now, why you're low energy? You're close to the nucleus. My friends in chemistry, to overcome this attractive force, you need higher energy. So you need to know this. Electrons leaping away from the nucleus need energy in order to overcome the attractive force, let's say, of their mom. Now, when they do that, my friends in chemistry, they become excited. Okay, your mom was with you all day in school. The next day she's not. What are you doing? Hi. Yeah, I can do that. You got more energy. Now, if you've got more energy, you're not going to exist in that way. Eventually, you're going to leap back to the ground state, low energy, and you're going to emit light or energy, okay, or spectra in colors. And those colors and light that's emitted is specific for that leap. And we can identify elements through spectral analysis. So all the questions that will come up, and you will see one, are here. What must occur when an electron in an atom returns from a higher energy state, whether here to here, or, just lost the one I had, or here to here, different orbitals. Energy is released. Specific amount of energy is released. Why is it specific? That's what they call quanta. The energy in the atom, only a certain amount. So specific has to be released. Okay? 2013. The bright line spectrum of an element in a gaseous phase is produced. Bright line spectra, that's the light. That's the light that we can use to identify. It's not about protons moving. Protons are never moving. They're well, they are vibrating, but they're not moving from one energy level to the other. Electrons move from what? If I'm giving off light, I have to be going from high to low to give off energy. I'm moving from high energy back to low energy. Same question. And my friends in chemistry, they can ask you this in part 2. In fact, my prediction, this will be a part 2 question. Somewhere in your part 2, I believe, they will ask you, why is light given off? And you'll just say what? Electrons are leaping from farther away to close to the nucleus. From higher energy states to lower energy states. Moving back toward the nucleus. All of that is all you need to explain that. That's what they are going to ask you, in my opinion. I haven't seen it in part 2, so you are due. During a flame test, hey, the flame test, you use different elements and they gave you colors. Hey, it's colored light. So lithium salt produces, who cares if it's lithium, produces a red flame. Okay, this red light is because electrons do what? Jump back toward the nucleus. Return to lower energy states within the atoms. Choice 3. These are the same questions. Over and over and over again. Mark my word, you will see something like this. Compared to an energy and charge of electrons in the first shell, or that, depending how you look at it, for beryllium, the electrons in the second shell have what? Well, if you're farther away, what kind of energy must you have to exist farther away? Must have higher energy. So, more energy. The farther you away that you can overcome the positive pulling force of your mom, the higher energy you are. In fact, if you have too much energy, you go far away. Right? Remember the story I told? Little Nuru was close to his mom, he's being controlled. When he had a little more energy, he went across the street and he was his own man doing some business. Then all of a sudden one day, he took some funny candy, he just ran away. He had too much energy, right? You have too much energy, the electron will do what? Move away. What do we call that moving away? The energy needed to move away. Rhymes with ionization energy perfectly. Perfect. You guys are rappers. Okay? Now, so we'd say same charge. Electrons have the same charge no matter where they are. And the second shell has more energy, number 3. I know it's hot as place you go when you go bad. Okay, 31. Here is an example of the light given off. Here's an example of a question you will see, probably. Which element is present in the mixture? Well, if there's a mixture of elements, these represent different types of, let's say, red, Roy G. Biv, different colors of different energies. You can identify elements based on their colors. So, element A is involved because all the lines of A are there. Who else is involved? Maybe A is not involved. No, A is involved. Looks like to me element D. Every line of D is there. So A and D, right? Oh, which one's not present in the mixture? My bad. So A, D, how about X? X is not there. So X is not there. Better read carefully. If I didn't read carefully, I would have got it wrong. Electron in a sodium atom gains enough energy to move from the second shell. If I want to put the fan on, will it be better? I have to talk over it. Let me see if that works. It might blow some of you guys away. It is brutal here. got pointed to the ceiling a little bit. Just move hot air around. Is that better? Does it feel a little bit? Okay. All right, so hopefully it keeps hearing me. Okay, because it's brutal up here. Okay. So an electron in the sodium gains enough energy to move from the second shell to the third shell. Second shell to the third shell. I don't care what, before I have it, all these markers will be gone. I don't know where they go. Oh, they're up here. Second shell to the third shell. I'm going farther away. So the sodium atom becomes what? What does ground mean? What kind of energy do you have if you're grounded? Low. That means you're back where you were originally. Excited means you must have gained energy. To pull away from the positive pulling force of your mom, you need energy. Okay? So it would be 3. An atom gets excited. These are the same types of questions. I want you to be able to identify them. I know they're not hard. Last one. Excited state. An atom moves to the ground state. The electron does what? We're going from high energy farther away because I need that energy to get there to go closer. No, not absorbs. Think about it. If I'm closer, I need energy to pull away. When I pull away, now I have the energy. Mr. Excited state is now going to lose the energy to go back. So if you're excited, you have high energy. And now you're going to go boost back to the ground state, like you're grounded. Okay, you're in trouble, you're close to home, low energy, you're not doing anything. Energy had to be emitted, and it moves to lower energy. Choice 4. These are not hard. Okay. Guess the last one I lied. A specific amount of energy is emitted when let's say electrons in an atom in a sample of an element returns to its ground state, even telling you in this case. This emitted energy can be used to do what? You can identify the element based on the type of light it gives out. That's what the other question was. Okay, so what we're going to do now is going to move around. And now I realize there's another great question that's related to this that should be next. So we're going to move back to that. So we're going to, I don't know what page this is, but find excited state. Notice the number here, 31. 1 through 30 goes the entire year, so you can bet your bottom dollar. Number 30 is a nuclear question. 31 is atomic structure. So this is electron configuration. Here are some classic excited state questions. Which electron configuration represents a selenium atom in an excited state? Okay. Classic excited state question. Now, first of all, I hear the word atom. I think what? Neutral, right. Now, if it's neutral, because I heard atom, protons equal the electrons. So the first thing I would do is I would go to my reference table. Let's go find selenium. And when I do so, and I'm going to get up close and personal here. Oh, where are you? There you are. Get up close and personal some more. All right. And let me just get closer. SB. We can do this. There we go. So selenium. Yep. Just getting it on the screen is a challenge. Selenium. SC, where are you? There you go. Let's focus this baby up. Okay. Now, so selenium. There is its what? Everything written on the periodic table is an atom. Everything. They do tell you what? They do tell you, is that a song? What? All right, sorry. They do tell you the charges they like to become when it becomes an ion. But this is an atom. The question said atom. So atomic number 34 means I have 34 protons and I have 34 electrons, right? So the first thing I gotta do is see who is jumping out of order. To be excited means an electron was at a position it was supposed to be, now jumped to a position it's not supposed to be. What I mean by that is, in order to fill this to 18, this has to be 8. Look at this, 2-8, 18, 6. You guys should know, in order to fill the second shell, you need to fill the first shell if it's ground state. Why? Electrons go to lower energy positions first, closer to the nucleus, right? Think of the nucleus right here. Then they fill the higher energy states in order. Kind of like if you had a room in your house and you had 3 friends. There was 2 seats that are comfy, cozy, and 1 seat that's awful. It's the futon that you pull up the floor with. Okay, you need to like flex your legs to stay on it. Who's gonna sit in the futon first? Nobody. It takes more energy to sit there. You're gonna sit in the comfy, cozy seats. So this is written as a ground state. So look at this, 2-8, 18, 6. They want you to pick this. I went to the periodic table, you know, something like what I see there. This must be the answer. But that's ground state. Ground state. That's going in order. I've got to show it jumping out of order. This is the wrong element. That's the next one. So looky here, party people. These 2 are excited. This should be 2-8, 18, 5. This should be 2-8, 18, 6. What's happening here, party people? I have 2 choices that are going out of order. You can't have 18 unless this is 8, unless an atom close to the nucleus jumped away. So we're kind of breaking the rules here. And that's what an excited state is. But these are ground state, these are excited. Which one is selenium? Because it's the atom, it's the one with 34 electrons. So you can count them to 34 or think with me. It's supposed to be 2-8, 18, 6. So what if electron jumped from here to here, what does it become? 2-7-18, 7. Choice 2. Classic chemistry problem a lot of people get wrong. And if you count, it's the only excited state. These are all electrons that add up to 34. Okay? You want to see my pen? I'm going to lose it 20 times. I lose my wallet 4 times a day. Keys. This is not a good thing. Oh, here we go. All right. January 2013. Same question. Why did I put it there? Because some of these questions will be exactly the same. And if you get them wrong, I will fine you this summer. Okay. Sulfur, excited state. First of all, which ones are ground state? Which ones are going in order? Before we look for sulfur, which one's going in order? This one, these 2. These guys, to fill the third energy cell, you have to fill the second. 8 fills the second, right? So these guys are excited. We want an excited state, so I know it's between 1 and 2. So I look for sulfur, party people. I look for sulfur, too much movement. Sulfur is 2-8-6. Ground state's given, they want you to pick that. I'm trying to get you to pick that. So what just happened, party people? Well, if it got excited, what happened? An electron from the second may jump to the third. So this becomes 2-7-7. Notice 7 plus 2 is 9. 9 plus 7 is 16. If it's an atom, it's neutral. protons equal electrons. It's the only one going out of order that equals 16. You guys get that? You're going to see that question. Okay? All right. Now, another common mistake. Let's go back to where we were. Sounds like another song. Okay. Again, for those that get this, I'm sorry you're sitting through, but I'm trying to make sure you don't get these silly ones wrong. And I'll tell you, what breaks 100 from a 98 to 100 is one of these silly ones. So you just have to see a lot of questions sometimes if you're at this point where you're going for a high grade. So I feel bad, but now I'm over it. Okay, similar chemical properties. Classic part 2 and part 1. Which element has similar chemical properties that are most similar to the properties of fluorine? Now, why would you have similar properties? Look at the choices they give you. They give you boron, neon, chlorine, chlorine, and oxygen. Let's go to the periodic table. Okay. What are they giving you? What do they want you to fall for? They give you boron. Boron's in the same what? Row, because he wants you to pick that. They give you chlorine. They give you neon. I guess I should move that over. Same row as well. That should give you a hint not to pick it. Oxygen and chlorine. So you've got boron, neon. Is it oxygen too? Oxygen. They're in the same row. Why would you pick a choice in the same row? So look at your questions. But these guys have the most similar properties. Why? What do they have the same of? Right. What makes them unique? Dmitri Mendeleev did not know about valence electrons. You know what he did? He saw that elements had similar chemical properties. So it's about the valence electrons. And this is a part 2 explanation. They will say to you in some problem, why does fluorine and chlorine bromide have similar properties? And all you have to say they have the same valence electrons. That's a key. That's something you probably will see, whether it's part 1 or part 2. Okay, moving forward. So of course the answer is chlorine. By the way, if they're in the same family, aren't they related? Hopefully. Okay? I guess there's some. Anyway, which elements have the most similar chemical properties? Who's in the same what? Column. Why is number 3 the answer? Because these are alkaline what? These are alkaline earth metals. So I've got magnesium, strontium, and barium. These all are in the same column. Bearing below. So 3 is the answer. Why same valence electrons? I want you to say, hey, I got this. I know this question. I saw it yesterday. That type. Where's the most similar properties? The ones that are in the same column. Oxygen and sulfur is your answer because they're both group 16 elements. Maybe. If I can do this, maybe not. Okay? You don't get those wrong. Chemical properties. What do you have to know about chemical properties? Chemical properties, you're changing a new substance. They're going to ask you some way, somehow tomorrow, do you identify a chemical property? Okay, real fast, real slow, real tall. Is this a chemical change? Is that a chemical change? No. What do we call this? It's a phase change. Now, what do we call this specifically because they love to ask what this is specifically. What kind of phase change is this? Sublimation if you go from solid to a gas. So sublimation. My friends in chemistry, they love to ask the opposite. What is it from a gas to a solid called? Deposition. Okay, in any case, real fast, these aren't real difficult, but they do pop up. chemical property. Whether you react or not, whether you can actually make chemical bonds. Think about physical properties you can identify without changing the substance, identifying the color, whether it's brittle or if it's undergoing a phase change, are all physical. You're not breaking bonds, you're just changing the distances between them. So clearly, number 4 is the answer. They can ask party people the chemical properties of a noble gas. And you would say their inability to react is a chemical property. Look at this one. This gets people all the time, these questions. Compared to a 26-gram sample of sodium chloride at STP, a 52-gram sample has what? Well, the density's not going to change. It's mass over volume. Bigger mass, bigger volume. It's a ratio of how the atoms pack. Different gram formula mass, that's when you add up the stuff. It's still one sodium and one chlorine. Same chemical properties? Yes. Why? Same chemical formula. Now, when does this change? When do the same chemical formulas no longer have the same chemical properties? When what changes? Structure. Structure is king. How many questions have you seen where they'll say this to you? Okay? What's different about these two? They're both made of pure oxygen. Do they have the same chemical properties? Both made of pure oxygen, you would say? No, because they have different structures. Hey, my resonance for my honors kids, right? SP2 hybridization alone there. Different structures. They can give you this classic question. I'm sure you've seen it. Carbon diamond. Carbon graphite. Why is graphite, which is on your pencils, and diamond, which of course you may wear when you're hearing, okay, or pierce your tongue. I'm not sure where you do that. Maybe you don't do that. In any case, these have different what? Structures. Notice in the graphite, the carbons slough off. That's why you can write with it. And of course, diamond wouldn't work. It is the hardest substance. Both made of pure carbon, different structures. Structure is king. Very important. You wouldn't wear the stuff in pencils on a ring, and you certainly would try to write with this. This, of course, is a guy's worst nightmare, by the way. All right. Moving forward. So, has different densities, have the same chemical properties for number 3. What identifies chemical reactions? Deposition sounds like what? Decomposition. Deposition is a gas going directly to a solid. So these aren't chemical reactions. You can't pick what? You can't pick phase change. Decomposition and synthesis are chemical reactions where atoms are being pulled apart and reformed. Okay. Again, always amazed by people getting these types of questions wrong. Atom, element, uniqueness. To be chlorine or not to be is the question. So if you're chlorine, what makes you chlorine? 17 protons, which they call the atomic number. Why? It's what makes the atom unique. So number 4 is the answer. My friends in chemistry, chlorine can have different masses. What do you call that? Isotopes. Same number of protons, different number of neutrons. So your neutrons can be different. By the way, okay, an atom of chlorine would have how many electrons? If it's an atom. I say atom, you say atom. So how many electrons would it have? 17. So if they had 17 electrons and atomic number 17, they'd have 2 answers there. Okay? So of course the answer is going to be atomic number of 17. These are easy, but I see people get these wrong. Number 31. Atom in the ground state has 2 electrons in the first shell, 6 electrons in the second shell. Here's the key. What did they say? What was the key in this problem? You say, I say, yeah, by saying atom, they're telling me it's what? Neutral. And the what? Protons, which are positive, have to equal the electrons that are negative. So if I know there are 2 electrons in the first shell and 6 in the 7, There's 8 electrons overall, which means I need what? 8 protons, because it's atom. Easy questions that people get wrong because they don't recognize that atoms are neutral. Protons equal electrons. Which statement about one atom in the element identifies the element? It can't be the neutrons. You can have different neutrons. Those are isotopes. It can't be the electrons. The electrons can differ. Those would be ions. Atom. The number of protons. That's what identifies the element. That, of course, would be hydrogen. Simple, but people get these wrong. I had a person who took this test, got a 98, they got one wrong. This is the one they got wrong. So no matter if you're an honest student or someone just trying to pass, these are questions you should not get wrong. Okay, what about this one? Number 6. Which substance of atoms, neutral, of the same element but different molecular structures? Can these ever be atoms of the same element with different symbols? So it's just 2. And I've had people tell me over the years, I didn't pick 2 because I thought it was too easy. There's going to be extremely easy questions on this. Don't overthink it. I didn't pick that because it's way too easy. Very easy, right? What? Different structure, different properties, but they're the same element. Number 7. 13 protons, 15 neutrons is an isotope of which element? Notice they're using the word isotope. What identifies the element? 13 protons. I wasn't that lucky, it's not up there. Atomic number 13. It's that simple. It's too easy. Too easy. There's going to be those questions on there. Okay, electrons gained or lost. This is in the part 2b. Which atom in the ground state has the same electron configuration as a calcium ion in the ground state? Okay, let's go find calcium. Here's calcium. Hello, everybody. Here's my calcium. Now, calcium loves to do what? Become what charge? +2. How did it become +2? Did it gain 2 protons? Yes. Lost 2 electrons. You can't gain protons. Good. So becoming positive means you lost your negativity. Mr. Grotsky, how are you? Fine. Are you happy? No. Are you sad? No. I'm what? Neutral. Lose my negativity? I get goofy or positive, okay? So yeah, this became positive by losing 2 electrons. Now, you need to understand this big concept. This could be part 2 right here. Why does calcium lose +2? Well, it's a big atom. Yes, metals are big. They can lose. Electrons are farther away, but it's 2-8-2. If it loses 2, it becomes like 2-8-8. Who's like 2-8-8? Yes, yes, yes. 2-8- can I do this? 2-8-8 is argon. You guys took Spanish today? Yeah. Just roll the R's for fun. Okay? So argon. Okay? And after tomorrow, all your tests are gone? Cool. Okay, sorry. Dumb puns are definitely included today. So yeah, why does chlorine become -1? 2-8-7 becomes, why does oxygen gain 2 electrons? To become 2-6 becomes, hey! So the reason why they become ions is to achieve what? Stable electron configurations. Okay? Moving forward. What's the overall charge of an ion? My friends in chemistry, it is no longer an atom. So now it's not neutral. But I become charged by gaining or losing electrons. That has 12 protons, 10 electrons. Classic question. Well, I'm going to do my math here. 12 protons is plus what in the nucleus? Plus 12. I got 10 electrons surrounding it. Each one's -1, right? So clearly I have plus 12 in the nucleus, surrounding it in some fashion. I've got negative 10 electrons. Do your math, you get plus 2. The charge of the ion. By the way, if you really wanted to get fancy, pinky up, 12 protons. Who's that element? Who's that element? I can do this. Magnesium. So my friends in chemistry, does magnesium lose 2 electrons? Atomic number 12. Okay? It all comes together, hopefully. Not a hard question, easy one that I see people get wrong. Moving forward. Lithium reacts with bromide to form the compound LiBr. Okay, great question here, because some part tomorrow, you're going to be able to figure out, is this an ionic or covalent bond? What is Li? Li is a what? Metal. Okay, it's off to the left. To the right, you have bromide, who's above the staircase. Iodine? I can do it. So So Br is off to the right. So metals do what? And this is important. Metals lose electrons. Remember the thing I gave you, hopefully? The catchphrases? Metals are losers. Maybe some of you guys can attach yourself to that or not. Okay? Non-metals love to listen to what band? We are the champions. Queen? Queen? Thank you. Okay? So these guys love to gain. Look at the charge. They become -1. It's the first one, it's the one they become most often. All right? So obviously there's going to be a transfer. So the metal, each lithium loses an electron and becomes positively charged ion. All right? You don't really need the bromide there, but you need to be able to do this. My friends in chemistry, they may ask you to draw a Lewis dot diagram, okay, of this. Lithium is 2-1. It has how many dots? Valence electrons are dots. Bromide. What is it? What's my bromide? 2-8-18-7, yeah. Valence electrons? That was weird. Nah, can't be this. Okay, so how many dots? 7. My friends in chemistry, that could be a question. What's a Lewis dot diagram of bromide? Br, 7 dots, 7 valence electrons. What's a Lewis dot diagram of lithium? They ask you for a Lewis dot diagram of an element. Yes? It's still an atom. Yeah, because that's not going to change anything, because the Lewis dot diagram is about the valence electrons. So whether I have carbon 12 or carbon 14, okay, they both have 4 dots, 4 electrons. Good question. So now, my friends in chemistry, what happens? This is important. This guy loves to lose because its electronegativity is very, very low. It's a big atom. Electrons are farther away from the nucleus. This thing is small. Electrons are close. So there's going to be a transfer, and it's an ionic. Okay? So how do we draw this? So bromide's going to grab this electron. So bromide is going to have, started out with 7, gains another. I do brackets and charges to show that lithium lost, +1, lost an electron. The ionic bond is between those two. You know what some people will do on a test? If they ask you to do this, they draw this. Mark my words. And I have to mark this wrong because you're showing sharing, and that's covalent. Question?
If you were to separate them, if you did put brackets,
If you separated them large enough, then I could see clearly there's no sharing here.
then you would get.
But that becomes dangerous because if you write them too close and I think is showing sharing, then I have to make it wrong. Brackets tells me that those electrons belong to this one, belongs to the other one. You don't need the brackets, but if you draw them too close and we think is showing sharing, we have to mark it wrong. Okay. Moving forward somehow. So lithium loses an electron, become positive, like all metals. Aluminum plus 3, how many electrons? Well, how many electrons does it have when it's an atom? How can I find that? That's my starting point. How many electrons, where did it go? How many electrons does it have when it's an atom? Yes, atomic number 13. So there it is. So it has 13 protons, 13 electrons when it's an atom. Now if it's plus 3, what happened to it? Lost 3. So it started with 13 and now has 3 less. So now the answer is 10. That's simple. It is that simple. My friends in chemistry say, Mr. Grodsky, I'm pretty good with these part 1s. Guess what? That question could be in part 2. The same question. They can have some blur, has nothing to do with this question, and say, hey, by the way, how many electrons does the aluminum plus 3 have? Or the ion in the diagram has how many electrons? Same skill, very important. Okay, moving forward. We did the excited state stuff already. I'm not going to do any more excited state. Okay. My friends in chemistry. Bonding is a stable or unstable state. What does stable mean? Well, I give you stable. Pretty low energy. Yes. That does mean stable. Stable means low energy, meaning once the atom has the 8, the octet, I can do 8, right? Once it has the 8, the octet, it's not going to bond anymore, so that's part of it, true. So if an atom doesn't bond anymore, it's not going to do anything. Not doing anything in that one position means stable. The rock outside, if you had a boulder in your house, boulder outside your house, okay? Don't bring boulders in the house, but if you have a boulder in your property, it's stable because it's not going to move, because it's going to be in that state, because it takes a lot of energy to what? To move it. Things that are stable you can lean on, rest on, and be assured it's going to be in that position because it's the lowest energy. Understand this. You must understand that stable means low energy. Your parents are stable. You can what? Lean on them. You can expect them, hopefully, to be the same person today as yesterday and the day before. The guy at the city in the train station that wants you to sell him his what? Rap album is unstable. That guy, you don't know what he's going to do. He has high energy. Unstable means what? You have high energy, and if you've got high energy, you're going to do something with it. You're not going to be in that same position. So, chemicals bond because they want to achieve low energy. At the end of the day, for those that hear me talk all the time, we don't do wind sprints. You know, it's getting to be 9:30, getting tired, I'm going to do gassers outside. Okay? At the end of the day, you do what? Put your feet up, you relax, you become stable. Chemicals bond because they want to fill their octets to get stable. If you're going to a stable state, you're going to low energy. So my friends in chemistry, when chemicals bond, when they become from free atoms to form a bond, energy has to be what? I'm bonding. I'm creating a stable state. I'm creating low energy. To get low energy, what must I do with my energy? Release it. So anytime a bond is made, always energy is released. Now the opposite, by the way, if it's being released, I'm going to write it right here. This is called an exo or endothermic reaction. You better be able to identify that. Energy on the product side is exothermic. Energy is being released. Now, if I draw the opposite, here I want to put the energy on this side. Bad planning on my part. Why? Well, if energy is released when you form a bond to get stable, it must take energy to move the boulder. So it always takes energy to break bonds. After we're done with the review today, let's go walk down to West Hampton to start breaking stuff. Will we need energy? Yeah, we'll need energy to break stuff. So if you forget all of this, it takes energy to break something. And if you understand that, the opposite is also true. So, to break a chemical bond, you always need energy. Why? Because if it's in a chemical bond, it's low energy, it's the boulder. To move a boulder takes an incredible amount of energy. Number 9. What occurs is two atoms of fluorine combine to become a molecule. You're forming a bond. You're creating a stable state. Stable's low energy. Energy has to be released. A bond is formed. Energy is released. You've got an octet now. It's low energy. As it gets a low energy, it's got to release it. Choice 2. Number 34. Classic way. This is bonds have to be broken. And if you didn't know, energy on the reactant side is endothermic. You need energy to break stuff. So bonds are broken, the reaction is endothermic. Choice 1. Same thing. Energy is absorbed as bonds are broken. It's the same thing over and over. Yes, Carol? You're like Charlie Brown's teacher right now. I can't hear you. Sorry, this is so easy. What's that? Multiple covalent bonds would be something like oxygen, who has 6 valence electrons. And it would need to make a pair of these. So oxygen is double bond. Carbon can make multiple because it has 4 valence. So it needs to have 8. Hydrogen can have multiple because hydrogen has 1 valence. So to fill the first energy level for hydrogen, it needs 2 electrons. It's filled. Nitrogen has 5 valence electrons. So it needs to share 3 more from another nitrogen in order to have stability. Triple bond. By the way, while we're talking about this, in N2, how many pairs of electrons are being shared? How many pairs of electrons are being shared? 3. But they could do this to you. How many pairs of electrons are being shared now? Still 3. A dash is a pair. They could say, be careful. They could say, how many electrons are being shared? And you would say, 6. Good. Okay, moving forward. Okay, these are diagram questions. Some people don't like these at all, so let's do them. Look at this question. Which diagram represents a mixture of 2 different molecular forms of the same element? Stop. You hear element. I think what? Same type of atom. Yes, we now know the atoms differ by the proton number, but in diagrams, if it's an atom of X, all I'm going to see is dark dots. Now, there's 2 forms of elements. There's monoatomic, and there's what? Diatomic. So look at choice 1. They want the same element, don't they? If I have the same element, I better just have 1 type of atoms. So it better be all empty circles or full dots. My friends in chemistry, there it is. all the same element. This would be a what? Compound. This would be a what? Diatomic element. They could say to you in the same drawing, which of the following represents Cl, a diatomic element? You would say here. Which choice tells me? Here's another question. A heterogeneous mixture of a compound and an element. Which one? A heterogeneous mixture of a compound or an element. Now, from an element, I'm a group with the same type of atoms. So this could be my answer. Here's an element, here's a compound, two more different atoms. So I have two choices. That wasn't the question, but I'm just showing you how they can use the same drawing. Yes? Okay, homogeneous is the same throughout. What you need to understand is there are two things that are always homogeneous, and they're called substances. And this comes up sometimes. I'll say to you, which of the following is a substance? Think about it. If you are a substance, you are one thing. If you have substances, you're a mixture. So to be a substance, you can't be a mixture because a mixture has substances in them. So a substance, okay, is an element which is made up of the same type of atoms, or a compound which is made up of two more different atoms bonded. Okay, now you're asking, how do you know if something's homogeneous or heterogeneous? The play with the homo and hetero is here. If you've got a substance, it's always homogeneous because if you're an element, same type of atoms. If you're a compound, you're a substance and homogeneous because you're made up of the same type of molecules. Okay, if I had this and then I had this, that would be a mixture. There's two more substances. And then there's another homogeneous part to chemistry. And it's linked by aqueous. That screams I have this compound mixed with water. Not a substance, it's substances. Now what's homogeneous about that? Anytime you have a solution, that means what? Something was dissolved. And I love this question. I don't have it up here, but they love to ask this now and again. How can I separate NaCl aqueous? And 5 out of 10 students say, ooh, you can filter it. If something is dissolved, can you filter out the solute that's dissolved? No. You have to boil it off, which, by the way, is a physical change. This is a what? Homogeneous mixture. If it's a homogeneous mixture, it is a solution. Something was dissolved. How do we separate mixtures? They're made physically, and they're separated physically. If you have a compound being made, they're made chemically. So this going to this would be a chemical change. Compounds are made chemically and they're broken apart chemically. Yes?
So is it always homogeneous and that's aqueous? Or,
Yes. If aqueous means something was dissolved, that means you just made a solution. And you can get a question that says, which of the following is a homogeneous mixture? You're looking for a solution, and that aqueous means that that's been dissolved. Then, as we're on this topic, they can say, draw the attractive forces in this solution. And you know that NaCl is an ionic compound. I call this famous boyfriend, famous girlfriend, but Na plus attracted by negative part of the water attracts the positive ion, and the positive part of the water. Earth to people, if you know nothing else tomorrow, water is polar. Water is a polar molecule. They will ask you that. Water is polar. And what dissolves what? Like dissolves like. Anything I'm talking about today is things that are on your test. They can say, hey, why does NaCl dissolve in water? Because they have similar attractive forces. Will this dissolve in water? Which is really this. Is this a polar molecule? Ooh, it's not a polar molecule because it's symmetrical. Water is polar, so that's the reason it doesn't dissolve. Okay? Why does ammonia dissolve? This ammonia, NH3. Why does this dissolve? It's polar, like dissolves like. Similar attractive forces. That's a part 2 answer. Hey, why doesn't this dissolve? Oh, because that's polar and this is non-polar. Why does it dissolve? Because it's polar and polar. Like dissolves like. Okay, is it absolutely true? No. For the regions, we'll go with it. All right, I'm spending time on these important little facts that do come up. Okay, continue on. Okay, which particle represents the arrangement of F2 molecules at standard pressure? Now this question was saying, hey, what phase is F2? They were saying to you, did you know what phase F2 is? Now this is kind of a trick question because they say it's 95 Kelvin. So the only way to answer this is go...
The table called the list.
Yeah, table S, the most underutilized table. Because I don't know this answer. I know at STP fluorine's a gas, and I can go over the ones that I know. But at 95, I've got to check its boiling point. So I go to table S. Okay, we go to table S, thank you. Okay, it has a boiling point or melting point. So the boiling point is 85 Kelvin. So what this is saying, this is above its boiling point, which means it must have converted to a gas. It's boiled already, right? Anytime the temperature is above the boiling point, you must be in the gas phase. So they're screaming to you, it's at the gas phase. Now what do we know about the gas phase? Does it take the shape of the container? Yes. Does it always fill the container? Yes. Even if you have one particle in a helium tank, you can bring back your helium tank and say it's filled. Technically, but I'll try that. Okay? It will fill the entire tank, technically. Okay? So that's of course your gas. This of course would be a what? Solid. Solids have a regular geometric repeating arrangement. What kind of entropy do they have? Ooh, another topic number that comes up. What is entropy? Disorder. How do you compare the solid to a gas? The solid has... Gas is higher or the solid's lower. This is a part 2 explanation, people. And of course, this is a liquid. Now, how do I know? The arrangement isn't what? It's not exactly 3-dimensional. Okay, or it's not a repeating arrangement. This would be a gas too. Now, so now we're down to 1 and 2. It's a good question. This is a gas, because it's filling its container. This is a gas. Which one is it? Well, they're expecting to know that fluorine is a Hofbrinkel or a Brinkelhoff, depending upon the teacher you have. For those that don't know what the heck I'm talking about, okay, neither do I. I'm just an actor. But Hofbrinkel are your what? Your diatomic elements. So all of these elements, okay, will be diatomic. So tricky, but the answer is 2. Okay, here's my key. Which particle diagram represents a sample of matter that cannot be broken down? My friends in chemistry, all of these can be broken down because there's bonds. This is just the same atom, and you get this question a lot, don't you? They'll give you the following question: which of the following can be broken down? And they might give you ammonia, silver, gold, and magnesium. This guy can be broken down because it's got what? Bonds to break. You can't break an element down to anything simpler. Okay? This question: who are elements? Elements are the same type of atoms. All the same, so 2 and 3. Okay, which substance at STP can be represented by this particle diagram? So this question is making you realize that this is a what? Solid. Now something, Mr. Grodsky, how is this solid floating? My kids saw Echo this weekend. I don't know, Netflix. I think it's floating, like they're looking down at it, I guess. But a regular repeating arrangement. So what they're saying to you is which one is a solid? Now you can go to table S, Courtney, and see which one has a melting point that's above 273, right? At STP is 273. If your melting point is above the temperature you're talking about, that means you haven't melted yet, and you're a solid. You could do that. Or you could do this way. Okay? Now I know some of you guys know the answer, but that's too bad. I'm going to go through anyway because it could be helpful. How do I know which elements are what? The phases. I can do this. Something like that. I call this the LL rule. Okay, if you're a loser, okay, like metals, take this L, put it this way. So this is 1L. Naphthol is the other. These are all my gases at STP.
Isn't there one just by itself?
Nope.
Oh, that's a liquid in it.
Yeah. So this is naphthol. This is 1L. This is the L. All of these are gases. The rest are solids at STP, excluding who? Yeah, PI. Bromide and mercury are liquids. Everybody else are solids. So if that could help you, you certainly can go to table S. Okay? Magnesium clearly is a solid. Okay? Now you don't have this page because I was still working on this today. Now, another classic problem. Equilibrium. You hear equilibrium, there's two things you think about. First and foremost, the rate of the forward equals the rate of the reverse. Never think equilibrium is when these guys are equal. You guys saw the tank demonstration. Okay? If I was to put an eyeball in this, all right, put an eyeball right here and look at it. Okay, this line is not going to change. Why? As fast as liquid becomes a gas becomes liquid. They'll ask you to explain this in part 2. This is a part 1 question, but they'll say, why does the amount of the reactants and products stay constant? Because the rate of the forward equals the rate of reverse. So there's two things to attach yourself to equilibrium. The amount of reactants and products stay constant. And that's because the rate of the forward equals the rate of the reverse. If I add a catalyst to this, does that change equilibrium? No. It makes the forward go faster as much as the reverse. Does a catalyst change delta H? No, it just lowers the activation energy or finds a what? Because they'll ask you what a catalyst does. And sometimes they'll ask you in not so many words. They'll say, hey, lipase is an enzyme that speeds up a reaction. We add it to a reaction. They're saying to you, hey, I'm adding a catalyst. And they'll say, describe to me how lipase increases the rate of reaction. What could you say? These are catchphrases on every test. They do what? Lowers the activation or finds an alternative pathway. In part 2, they're asking for the same stuff. Okay? So I'm going to put up a test here. I'm going to close this out. I ran out of time to make any more, but I'm going to put up a test here. In fact, would you rather me go through the reference tables? What do you want me to do? I have a crash course that goes through reference tables, but take care. Good luck.
Right here. If you're right-handed,
Okay, let's do the 32. Classic question. What is hydronium? Man, that sounds like hydroxide. Hydroxide, hydronium. Where can I look? Table, what the heck is that? So I go to table, what the heck is that? Table E. Zoom, zoom, zoom in. Autofocus it. And of course I get everything else but the one I want. Hydronium. People make this mistake all the time. Hydronium. What is hydronium? Where does it come from? Acids. So you hear the word hydronium, you think acids. You hear hydroxide, what do you think? Bases. So hydronium. What happens to the pH? Well, first of all, I'm increasing the pH. Am I getting more basic or acidic? Basic. So this has to do what? Which is from acids. Has to decrease. By how much? By how many units? 1. Remember, pH scale is a logarithmic scale. Here's a part 2 question I believe you will see. I'm only guessing, I haven't heard the test. Okay, watch this. I've got a pH, it could be a diagram. Maybe the pH is 3. Okay? And maybe the diagram, the pH goes to 6. And they can ask you what's happening to the hydronium concentration. If the pH is going from 3 to 6, you guys know it's getting more basic. So what's happening to the H3O+? If the pH is rising, you're getting more basic, and this is due to acids. This is decreasing. How much? Between this and this is what? 3, right? But it's 10 to the 3. It's a logarithmic chain. So it's a decrease by a what? 1,000 times. If I go from this, a pH of 2, pH of 3, going to pH of 2. What's to 1? What's happening to my H3O+? It's increasing how much? What is this? 10 to the 2. So it's 100 times. Sometimes they'll use the word 100-fold. Yes? Okay. Where am I in the test? 41. I'm getting close to the end of the year. Chemical reaction or nuclear reaction? Nuclear. How do I know? They're giving me numbers top below. Mass number, proton number. Transmutation is the word we use. Is this natural or artificial? So you're going to see this. Artificial and natural. Yes, artificial, because in nature, by itself, within its particles, you would say it's natural. In order for 2 atoms to collide, to create this, you need a particle accelerator. You don't go into a field, pick the berries, gather the nuts, and pick a particle accelerator. It's not natural. You've got to build a piece of equipment. So, attach yourself. 2 things on the reactant side is artificial. Okay? Christmas in July. Where am I? Okay, let me get this here. What is this question? Classic question. If they have the same molecular formula, what does that mean? What are they? Isomers. Iso means same. There's isotopes, same element, different mass number, different number of neutrons. Isomer, same molecular formula, different structure. These are your isomers. This is C2H6O, C2H6O. Now these have different structures, so they have different what? Chemical and physical properties. One could kill you, one you could ingest. Okay? Important that you recognize that. Moving forward. What's happening here and what's happening here? That's the ones they always ask about. What's staying the same? Another word for temperature because we may not even have it here. Average kinetic energy is temperature. They love to pick. So, which intervals is the potential energy decreasing and the average kinetic energy remaining the same? The average kinetic energy is remaining the same because temperature is the average kinetic energy. Now, potential energy is decreasing where? Every segment. I always tell my students, what's the general flow of the curve? Going up or down? Down. That means you're losing energy. If you lose energy, doesn't your potential drop? If my kids get sleepy, what's their potential to act out? Decreases. So it's decreasing in every one of these segments. It decreases the most here and second most here, but potential energy is not measured by a thermometer. Average kinetic energy. So we would say the average kinetic energy remains constant in B, C, D, E. But the potential energy is decreasing. Okay? How in the world would I do 44? Yes? Doesn't matter. They're the same. Totally good. How do I do 44? Yeah. Courtney, you're killing it today. You're doing great. You've been working at it. Awesome. Yeah, table J. 7 out of 10 students who take this don't know where to look for this. Okay? Huh? Now, what does spontaneously mean? I think some of you guys said it. Spontaneously means there's a pathway, that it can occur. Non-spontaneous means it can occur under the current set of conditions. So what we're saying is which one will react? Now, think about this for a second. If I've got something who loves to oxidize, sodium explodes in water. Gold does not. The one who likes to oxidize better is the one who will what? Oxidize. All right, now in this case, they're dealing with ions. You need to understand something. Standalone elements can only oxidize. In this course only, if you have ions of the element, they can only reduce in this course. So zinc plus 2, if it's spontaneous, it's not a standalone element. Talking about can it react, which metal will spontaneously react with zinc plus 2, so let's put it up here. But not with an Mg plus 2. Now think with me. If these things are ions, they can only reduce. They can only reduce if they're positive ions in metal in this course, right? If I am magnesium, what can only a standalone element do? Oxidize. Metals that are 0, atoms, neutral, protons equal electrons, can only become Mg plus 2. If you put it up there in the reference table, you will see that atoms of metals only become positive. Okay? They only become positive. So if they're positive already, they can only become what? standalone metal back, but they've got to gain electrons. So these are reducing. And in table J, very simple, I'd love to get into more of it, the ones who oxidize are always above the ones who reduces. And the answer to that is why? Because if I'm a metal, I like to lose. Metals are losers, okay? So they like to reduce, oxidize. So the ones who oxidize the best are on top of table J. So if I look at my choices here, magnesium oxidizes above zinc. So if magnesium is going to oxidize, zinc will reduce. What's the question state? Which metal will spontaneously react with zinc plus 2? So if I'm going to react with zinc plus 2, that means it's going to reduce. That means it needs something that what? Is going to be above it. Magnesium needs what? Something that to react with that's what? Above it. Magnesium and zinc both can what? Have to reduce. The one who oxidizes is above. So I need something that's above zinc but below magnesium. If you don't like that, in between. So what we got? That one. A lot of explanation there. Okay, but good job for figuring that out. That was table J. What else do we have? Like this question. First and foremost, party people, this fission or fusion. What does this 2 mean? What does that 1 mean? Yes. And couldn't I write it this way? Couldn't I write it that way? Yes, it's the same thing. So don't like, oh my God, I don't know what he's talking about there. Hydrogen 1, they're giving you the mass number. They're giving you the mass number. Isotopes. Fission or fusion? Fusion. How do you remember? When something fuses, it comes together. Light nuclei are coming together to make heavier. What's the other one you have to remember? Remember this and that? What if you have uranium plus a neutron makes barium, krypton, let's say 3 more neutrons. Big atoms being split by a smaller one, that's fission. Okay, which phrase describes this reaction? Chemical reaction? No! Where are we on this test? Where are we? They love to mix in chemical reactions. 48, we're at the end of the test in part 1. You're in nuclear area. Okay, not a chemical reaction, it's a nuclear reaction. My friends in chemistry, forget this. Unlike a chemical reaction, the masses will not equal up to equal the other. There's a little bit of mass missing. Okay, maybe your teacher talked about it. Okay, E equals mc change, means square root of c. Mass times the speed of light squared. There's a little bit of mass missing in a nuclear equation. So we say that the mass is being converted to energy. What kind of energy is given off in a nuclear reaction compared to a chemical reaction? Tremendous. You know why? The little mass missing times this gives you a lot of energy. Okay, that pops up. And they also could ask you, compared to fission, how much mass is missing in fusion? And you would say there's a lot more mass missing in fusion because there's more energy given off in fusion. These both give off more energy than a chemical reaction, but nuclear fusion gives off a lot more energy. I always said a fistful of uranium in fission can run New York City for about a month and a half. A glass of water has enough hydrogen to run New York City for about 8 years. Okay? Important. I'm going to show you this because it pops up once in a while. Anyone know what this is? It's Part of the curriculum, yes. Chromatography. Chromatography is how we separate, let's say, a mixture based on solubility. Solubility is a physical property, how well something dissolves. So we have a mixture of food coloring. It's got a couple different chemicals. Some want to stay with the polar silicates. Some want to go with the mobile phase. Just be aware. How do we separate mixtures in this course? We can evaporate the water. Boiling the water is physical. Right? So evaporation, they'll say to you, hey, I've got a saltwater solution. How do I get the salt back? Boil off the water, evaporation. What if I have liquids? Like I have kerosene and diesel fuel. They're both liquids. They're both a mixture. Remember the word distillation? You need to work. That can pop up in part one. It can say, hey, which of the following represents a way that I can separate liquids in a mixture? And they can write titration, filtration, distillation, chromatography. Distillation. I don't know if you guys did that in class. We had Coke. We boiled off the water from Coke. Okay, well you do that with fossil fuels. You'll see that sometimes. Chromatography is the one. Now I did this in class when I did the chromatography of the grape Kool-Aid. I separated the red and blue from the what? From the purple color. This is one that people forget. Okay, titration is the acid and base. All right, important. I don't know if you'll see it, but it's the one that could be a 100 breaker. All right, I'm just trying to show you that. All right, enough said about that. Balancing reactions. Chemical naming. Let's go through that. Zinc carbonate. Now what the heck is a carbonate? The first thing that I think about when I chemical name, I think about the ending. If I see an IDE ending, if I see an IDE ending, which I don't in this case, that makes me think binary. Binary. Look at the end. There it is. What does binary mean? What if I have this? KCl. What do you call this? Potassium with chlorine becomes potassium chloride. Now, if it's ternary, the ending will have the ending from table E. So, zinc is the element. So I write zinc. Really good strategy to write the charge it becomes. When you go find zinc on the reference table, periodic table, you should find that zinc becomes +2. You can see that, probably can't. So +2. Maybe. We can find zinc. +2. Okay? So I put that charge. What the heck is a carbonate? Another table. And that's table E. I call that the what the heck is that? What the heck is a carbonate? So I go to table E. And it's a CO3 minus 2. I want to show people this is where they need to look. So I find a carbonate. Not just the one. Christmas in July, where are we? Carbonate, CO3 negative 2. Now, this one is +2, this one's -2. I need what kind of formula for salts, empirical or molecular? Because people say they're robots, Mr. Grotsky, crisscross, and some people would do this. And that'd be wrong. It's a 1-to-1. When you do a chemical formula of ions, ionic, salts, you have to have the lowest ratio. So it's zinc carbonate. Now, I need to review this. People will get this wrong if I don't. What if I said to you, what is the chemical name of this? First and foremost, it's not copper nitride. If it was copper nitride, it would be binary. So what the heck is that cluster? Nitrate. Now what charge is nitrate? -1. Must be copper. But if you do this, it is wrong. Right. Unlike zinc, zinc only had one choice it can become. Copper can become +1 or +2. So because nitrates are -1, and there's 2 of them, -2 overall, this copper must be +2 overall. Since copper has 2 choices, then Roman numeral 2 is not for the second choice. It represents exactly the charge. So this would be copper, Roman numeral 2 nitrate. People get that wrong all the time. So if I said to you, I have lead 4 sulfate, that means what charge is the lead? Do I look for the 4th charge? No, it's lead is +4. Sulfate, what the heck is a sulfate? I go to table E. SO4, -2. Crisscross my applesauce, and what do I get? A mess on the table, I know, but I'm going to get 2 of those. Now, okay, just don't forget what that's all about. That'll pop up and you're like, "Arr!" Okay? What else do we get in these tests? Common questions. And everything that we're doing could be part 2 or part 1. 26. Who is an electrolyte? Important implications here. Who is an electrolyte? By the way, these are electrolytes. Why? What did I just draw here? Salts, ionic compounds. And what do? What does salts break apart into? Lift that important word. I want to draw it subtly. Now, you should be getting my hint. Excellent. You're so intuitive. CSI, here you come. Sherlock back there. Okay. What makes free ions? 3 things. Now, first of all, yes. Go ahead. First thing, soluble salts, ionic compounds, like NaCl breaks apart into what? Na+, Cl-. So salts. Acids. HCl does what? Breaks apart to H+, Cl-. And bases. NaOH breaks apart into what? Na+, OH-. My friends in chemistry, we're looking for salts, acids, or bases. When an H is written in front, it's screaming to you, I've got an acid. H in front, screaming to you, I've got an acid. These guys give off H+, there's my acid. There's my answer, sorry. Acid. Okay. Oh, they weren't asking. Wrong question. Okay, which compounds are electrolytes? Okay, I see an OH here. So this must be an base. No, this is an alcohol. Anytime you have carbons and hydrogens, that's your R. Alcohols are not acid, bases, or salts. That's a molecular compound. It is a non-electrolyte. We'll get back to that in a second. This is an acid. This is not your answer. Not a base. Alcohol, not a base. Molecular compound. OH with a metal. That's a base. That breaks apart to OH-. Acid. 3 is your answer. Okay? Now, we know about non-electrolytes. By the way, while we're on the topic, it's like delayed. 3, who else conducts electricity? Metals, because they have 3. And sometimes the catchphrase is mobile electrons. if your electrons are free to move, solid metals can conduct. Can solid ionic compounds conduct electricity? Hey, this is a salt. This is NaCl. This is a salt. I said salts, acids, and bases can conduct electricity. Can NaCl solid conduct electricity? No. No, because it doesn't have free ions. And this is a point or current you love to talk about. Ionic compounds are only electrolytes when they are liquids or aqueous. They love to ask about that. This solid salt does not conduct because the ions are not free. Solid silver, solid copper, solid aluminum, they have mobile electrons. It's important that you recognize that. Now, you notice something, party people. This is sodium chloride, or sodium fluoride. It's a 1-to-1 salt. Which one is the metal and which one is the non-metal? By the way, it's ionic. Is the small one the metal, or is the big one the non-metal? Trick question. Because these are ions. And this is another big topic that comes up. In order to become Na plus and Cl negative, what had to happen? What had to happen? In order for Na to become Na plus, what had to happen? Had to lose an electron. What do we call that? Rhymes with oxidation perfectly. All right, perfect. What did chlorine have to do? Gain an electron, get reduced. Now metals start out big or small. Look up here. Big, electrons are farther. Corey, stay with me, kid. Okay? Metals are bigger. They're losers. Electrons are farther away. So this thing starts big and gets smaller. This thing starts small, gets bigger. Why? Here's what you need to know. By the way, so the elements or the ions that are smaller are the ones that lost electrons. So the blue ones is the sodium plus. The chlorine is a Cl negative. And you need to know what happens. When I lose weight, I get smaller. When I lose electrons, it gets smaller. They ask you in part 2, why does the atom, why is the atom bigger in an element compared to its ion? You just say, I lost electrons. Answer, why is the element smaller than the ion in a nonmetal? Because I gained electrons. Gain weight, I get bigger. Okay? How do we identify a redox reaction? Standalone. Okay, let's go through this test. I don't even care. Let's look for reactions. Is this a redox reaction? Yes, it is. There's a 0. There's a 0. They could ask you for what kind of reaction is this? It's redox. Is this a redox reaction? It's a nuclear reaction. Silly rabbits. Ooh. Is this a redox reaction? Darn right it is. It's 0. So if you're caught in a dilemma in part 2 where you forget what the reaction is, okay, standalones are 0. Now my friends in chemistry, what are these parts here? First, exo or endothermic curve? How do you know? Because the energy of the products, we start with reactants. This is a total energy. When I look at a potential energy curve, I first evaluate how much am I starting with, that's the potential energy of my reactants. Then I see how much I end with, that's the potential energy of my products. The difference of where I start and where I finish is what? Delta H is correct. Now, here's something that pops up a lot. They'll say to you, which of the following choices represents the delta H of the reaction? They'll say the activation energy minus the delta H. They'll say the potential energy of reactants minus the activation energy. My friends in chemistry, delta H is the potential energy of the products minus the reactants. Why? Because I want to show a positive value. Can everyone see that this is a delta H is going up some number? I'm starting here and going up. The change in heat is going up. To show a positive value, I want a positive result. So if this is 100 and this is 60, 100 minus 60 gives me plus 40. So products potential minus reactants potential. That comes up in the multiple choice a lot. What is number 2 representing? Rhymes with activation energy. And how can it get lowered? Catalyst, right. Okay, enough said about that. How many times, party people, do they ask you, how can you change the rate of reaction? What are your choices? Add a catalyst. Change the temperature. Increase the surface area. Why does all those things increase the rate of reaction? Because you're increasing the number and frequency of the collisions. What's an effective collision? It's a collision that creates a bond or breaks bonds, but it's a collision that has not only correct orientation, but enough kinetic energy to overcome the attractive forces. So you have to have enough energy and you have to have right orientation. This one is a table I ratio question. Per one of these, that's the energy. So for 2 of them, you 2 times that. Okay? Okay. What kind of reaction is this? You see a standalone? Redox. Now, if you're in part 1, they don't give you a redox choice, you have to know this. This is unsaturated or saturated? Which means under the amount of H's. You should be adding 2 more H's here, but because the carbon makes 4 bonds, it's under the amount. This Br2 attacks the double bond. My honors friends, it's attacking the pi bond, just extend it outward. But once it attacks the double bond, it opens up the double bond into a single bond, which means you can add 2 more to 2 different atoms. This is called addition. So you can get this in part 1. They can say, what kind of reaction is this? They won't have redox. They'll have substitution, they'll have addition, combustion, fermentation. This is addition. Everything adds. What is substitution? If this was saturated, one would come on and one would have to come off. And you'd have 2 products. What's an empirical formula? Lowest ratio. Very good. Is this a redox reaction? This is -1 plus 1. No. The charges stay the same. Okay?
Why wouldn't it be like a endothermic or oxidation?
Oh, well, yeah. I could accept endothermic. Good point. If they asked for this reaction and you know the heat was on this side, I have to accept endothermic. Absolutely correct. Thank you. You could also say it's decomposition, correct? Okay, look at number 64 for a second. When they ask you to explain it a certain way, you better follow that. Explain in terms of ions why a 10 milliliter sample of a 0.3 molar aqueous dissolved with water is better conductor, better electrolyte than the same volume with less stuff. This one's a better electrolyte because it has more free ions. 0.3 has more dissolved ions than 0.1. It has more ions. The more ions you have, the better electrolyte you are. This stuff is all over the place. I'm not... Now, yes? Saponification is a reaction, and I've only seen it once on a test, but it's a reaction we take glycerol that has esters, and you split it with a strong base to make a soap molecule. It'll be a big reaction where you have glycerol. You have a triglyceride. And these are a lot of C's that keep going. And these are the H's. Now what happens, you add a strong base. That's going to split that, 3 of them, so you can make 3 of these. Here's an O negative. And we keep going. The Na plus from the base hooks up here. What you're going to have is 3 of these. Once these split, you're going to reform the glycerol, which is a trihydroxyl alcohol. And this is a soap molecule. Here's the polar head that it can interact with the water. Here's a non-polar tail that pulls the fat off. It's a big organic reaction. They kind of give the hope, soap saponification. Okay, now, my friends in chemistry, you get to part 2, you're tired. My suggestion, just my little old tall suggestion, is go to the questions first. To read this entire diagram, look at this diagram and says, what the heck am I looking at? Do not psych yourself out. Tell yourself, if you're not figuring out the problem, there is always an easy what? For every single one of these questions, there's an easy answer. So you may not recognize that this is an electrolytic cell. Who cares? Go to the bottom. Identify the component required for electrolysis of molten that's missing from the cell diagram. Okay. They're saying electrolysis. Electrolysis requires what? Electricity. So you're missing the battery. Now some people say, oh, it's missing a salt bridge. Salt bridge is for a voltaic cell. It's a battery. So you can see how you confuse this. This would not be in the same cell. So this is a battery that's needed to do this. Now if you didn't know that, maybe you go back and read. Okay? We're not saying anything in terms of needing energy. So electrolysis, and this could be a part 1 question. How is electrolysis different from a voltaic cell? Voltaic cell is a battery. Batteries do not need batteries that need a battery that need a battery. Batteries are, what's the word for S? Spontaneous. If they said to you, how is a voltaic cell, a battery, different from electrolytic cell? Batteries are spontaneous. They work by themselves once they set up properly. This is not spontaneous. This needs a what? Battery to force it to happen. Okay? Also, voltaic cells, batteries, they're exothermic. This and that. Right? This is endothermic. It needs energy. Something to think about. Identify one metal from the past that is more active than carbon. And one metal from the past is less active than carbon. Okay? So we go to the past. Some metals, such as zinc, lead, iron, and copper, can be obtained by heating their oxides with carbon. So if you can attain them by heating their oxides, I mean they're all, what? More reactive than carbon. Okay? We just told you that in the reading. Any one of those. If you didn't even understand it, it's right in the reading. Weird question, I know. I'm told. I'm losing you guys. All right. I've covered a lot of different topics. I feel like if I keep going, I'm just going to just lose you some more. So I'm going to end this now. Is there something you need me to cover? Something that's giving you some headaches? For those that I haven't seen before, and there's a couple of you there, I do have something called. At this point in time, okay, what you need is get a good night's sleep and a good breakfast. If you're going to review, you look at some more questions, but honestly, you're not going to learn everything you're going to need to know. My focus today was about identifying things, okay? And hopefully you're able to walk in tomorrow saying, oh, it's that kind of question, all right? And again, here's another suggestion. If you feel like you need to do more, okay, go to my YouTube channel, click on one of the tests. I'll walk you through the entire test. I could have done that here today, but I felt like if I did that, it's a waste of time. You can do that with me at home. I wanted to show you how similar questions, okay, pop up all the time. All right, and if anything else, good luck, all right? Rock on. Yeah, rock on. See you later. Yep. No, I am. I just was trying to figure out my schedule.
5:45. I mean 4:45.
4:45. You might. Yeah, that's what I saw. You're going to be after 4:45, 5:45, 6. Okay, 6 for you then. Okay. Hey, listen. Right on top of some hot questions. Awesome. Oh, awesome. You got it. Good luck, guys. If you have to overthink anything, don't overthink it. You're not in class? None of this knowledge. So in the basics of what you learn in chemistry, there's never going to be a question like the last question you test. It's always going to be an easy answer. So some of the sort of ridiculous things that it might really, really bother you, or something that be true, is a lot of it. Some little word in color piece in, and you'll be like, yeah, there's nothing. But today I was going over kind of again. For instance, honest people like which the following nuclei is used for identifying thyroid disorders. Iodine 131 is one of the exact question that bothers people. All of this, honestly, is straightforward. There's no trick question. There's always an easy answer. So if you've done your due diligence, do that. So you're one you have to overthink. No, overthinking would be wrong. All my concepts. All they want. You know, and if you're feeling uneasy about that, have me walk you through the entire test. So you figure out the biggest test you have to done. And when you just do questions you want, just walk you through what you see. And maybe you don't want the experts. Maybe you just want to do 1 through 50 and then see if you got wrong or not. Just when you walk you through, you'll see, wow, this is the answer for all of it. You know, when I had the honor sections, I had kids who would tend to get things wrong because when I think that there's an extra crazy question. Yeah, and just keep it like today, although it looked like I was working on multiple choice, I was really working on part 2 as well. As I'll say, you know, why is this electrolyte more than 3 ions? Why is the atom even bigger than the electron? What do you need? You don't, once you start writing a paragraph, you leave yourself open for saying something that's not correct. But short to the point. So take a part 2. Take part 2 now until before you go to bed. And I'll walk you through the part 2. Do them or I mean walk you through like, oh yeah, that's all they want, You find okay. And it's the same concept in part 1. It could be a part 2 in one test, it could be a part 1 multiple choice in the other. Same concept. So think about it. What's the concept of how many questions? So when you do some tonight, for today, this afternoon, think yourself, what's the concept you want? I'm always focused when I go through, here's the concept they're after. That's it. Once you start seeing that's the simple concept, it's like, okay, that's all they want. Never going to give you some convoluted question where you have to explain. Most of the time, you can explain in 3 words or less, or 2 seconds. Even when they give you lines, sometimes it's hard to, sometimes it's simple sentences is all you need. Alright? So yeah, so be positive and say, what's the concept behind this? What's the easy solution for this? If there's not an easy solution, then it's not the Regents Chemistry is. Okay? Good luck. You're welcome. Sure. well, things in nature tend to always go from high energy to low. You've got high energy. Because a rock that's higher on a cliff has higher potential energy. Because of gravity, it's got the potential to fall. A rock on the bottom of the cliff has no potential energy with respect to the height. So I use that. So a rock on top of on the edge of the cliff at some point is going to fall down. So it has the potential to do that. Okay? So things in nature that have higher energy, even higher potential, generally work themselves out to lower potential. The heat flow of the universe. Doesn't heat travel from hot to cold? Well, from high potential to low. High stored energy eventually comes down. All energy drops lower. Now, that being said, things in nature tend to go from a big rock to a small rock. So entropy also increases as you go. Without any effort, this room would be a mess. Because I put tremendous amount of effort in this room, it's not. Entropy is taking over this room. Naturally, I didn't have to work hard to make this happen. So things in nature become more disordered. You don't clean up your room, clean up your yard, clean up the road. You'll be living in a mess. You're constantly fighting it. You have to get energy. So in any case, entropy is always increasing. And things in nature with high energy want to become low energy. Don't we want to become stable? Yes. That's what we got. And you've seen that question before. See you guys. Good luck. Alright. Hopefully I covered enough points. I mean, I could have went line by line, but I think I wanted to show them how. Today was about the I was not going to spend time on breaking down electrolyte cell. I wanted to say these are questions you have to get read. Yeah, that's all about getting kids today. I have a girl in our question private. She was like banging out questions today. I'm like, wow, you know. But I'm worried about. I didn't see Sarah. I didn't see Kelly. I didn't see Kelly. Maybe you're you. No. Able